Hey, it's Mr. Allred, and I'm here to talk about rational functions, where we will talk about vertical, horizontal, and oblique asymptotes, which our ultimate goal is to graph the functions, but to make sure we understand the characteristics that determine how those graphs behave. So, not just picking up a graphing calculator and mirroring a graph from there, but to actually be able to pull these things from the function that we're going to see. So, first question is, what is a rational function? A rational function is a function with a variable in the denominator. We could be more specific, but I think this will be okay for us. But what this means for us is, once we put a variable in the denominator, that our function will have a domain issue. And just to very quickly make sure that's clear, the first one here I have is f of x equals the fraction 7x plus 3 over 2 minus x. So we do have a variable in the denominator, and we can very quickly kind of remember how we get to these domain issues. The domain would be that 2 minus x cannot be 0 because we can't divide by 0, so we cannot use 2. So the domain of this function is x cannot be 2. The second example here, f of x equals the numerator x squared plus 5x plus 4. The denominator is x squared minus 25, so there's that x in the denominator. So again, I can set that denominator to not be 0. And I can solve this many different ways, but this is a difference of squares, so it factors into x plus 5 times x minus 5. So I can honestly see that I had the domain issues where x cannot be negative 5 or 5. Okay. So both rational functions. So let's see where this leads us. We want to talk about these domain issues and how they impact the behavior of the graph. So the one thing we're going to talk about with these domain issues is vertical asymptotes. So I've got here that domain issues usually create vertical asymptotes, which are vertical lines where the outputs get extreme as the inputs approach the domain issue. And I also have here that graphs never cross a vertical asymptote. That's a little piece of pro information there. But the function here that we're going to look at, just to kind of demonstrate what's being said, is f of x equals x plus 2 over x minus 3. And if we take that denominator x minus 3, we'll find that the domain issue is 3. We cannot plug 3 in this function because it would be undefined. So more or less what my long sentence up here is stating is that as we get close to 3, which is right here, it does not exist, but what's happening as we get closer? And I see a typo here I need to correct as I go through. So first of all, I need to get this word out. But down here, I'm going to put in numbers close to 3. So 2, 2.9, 2.999. And you can calculate these, but what we actually have here as we get close there is when we plug in 2, we get negative 4. 2.9, which is closer to 3, goes to negative 49. And 2.999, which is even closer to 3, actually goes to negative 4,999. So almost negative 5,000. So over here in my graph, just kind of highlighting negative 3 the best I can. Right here. We'll see that as we come toward 3 from the left-hand side, those values get very negative. And if you read it from the right-hand side, coming at it, x equals 4, x equals 3.1, x equals 3.001, you see those numbers get really large, which you can see on that graph. So usually what we do here, and sometimes colors are not as available as others, but we put a little vertical dotted line here to kind of show the behavior that our graph is getting close to that as our graph gets close to x equals 3, that the graph is going to get extremely large or extremely small. So the red line here, which is the graph, does not cross over that asymptote, but as we get close to it, the values get extreme, which means really large or really small toward negative infinity. Okay? So that's what we're trying to say here. If I put numbers closer and closer to this domain issue of 3, I will get numbers extremely large or extremely small closer I get towards positive or negative infinity. Okay? So let's see here. We're not going to worry about the behavior just yet. We're just going to try and identify some vertical asymptotes. So the first one I have here is find the vertical asymptote for f of x equals numerator 3x squared plus 2, denominator x squared minus 5x minus 6. So we have a denominator, x squared minus 5x minus 6. That cannot be 0. So this one here actually factors x minus 6, x plus 1, I believe. So we get that the domain is x cannot be 6, x cannot be negative 1. Double check this before I go on. I think that's right, yes. So we'll say the vertical asymptotes are x equals negative 1, x equals 6, because these domain issues are the places that we will put the vertical asymptotes where it can get really extreme. So over here on the graph, just to make sure we understand what we're doing, I'm going to put these dotted lines in. So a dotted line over here at x equals negative 1, the best I can, and a dotted line over here at x equals 6. And I'm doing the best I can to get them straight. Okay. Alright, so let's do another one. We're going to complete these graphs a little bit later on as we find all the characteristics, so we'll keep returning to these examples. The vertical asymptote, this example is f of x equals 5x plus 2 all over x squared minus 36. So again, we're going to focus on that domain issue. Denominator x squared minus 36 cannot be 0. You can factor this if you like, x plus 6, x minus 6. So you get the domain cannot be negative 6 or 6. So the vertical asymptotes are the vertical lines where that happens. X equals negative 6 and x equals 6. So we'll put those in. Somehow we got 6 again. Let me, I guess I'm about as heavy as I'm going to get there. Maybe I just need to take the time to make sure they can be seen. So I'm putting it in over here at 6, and I'm going to put one in at negative 6. So that means from the graph example that we had, that as we get close to these two vertical lines, our graph's going to go up or down on both sides of it, fairly extreme. Okay. Okay, let me highlight this down here just so we know what's there. Okay, so moving right along, the next example here. This one here, we're going to find the vertical asymptotes for numerator x cubed plus 3x minus 4 all over denominator x minus 5. So we'll look at the domain issues. X minus 5 cannot be 0 because that's the denominator, so the domain issue is x cannot be 5. So that leaves the vertical asymptote. There's only one of them here. X equals 5. So I'm going to put that on my graph for later purposes. I just want to know where they are. And you could have multiple vertical asymptotes in your graph. You could have one or more, okay, because you have to have at least a domain issue for this to work out. The last example for vertical asymptotes is the fraction 3x squared plus 2x minus 4 all over x plus 2. So again, we'll look at that denominator. So the denominator x plus 2 cannot be 0 because that would cause an undefined situation. So the domain will not let us use negative 2. So the vertical asymptote will be x is negative 2. And we'll come over here and put that on our graph. So it's a vertical line. So the actual asymptote that we're making is not an actual point or an actual part of our graph. It's just kind of helping us demonstrate the behavior of the graph. So our graph's going to get close to that dotted line. Okay, we're going to pick these back up with some more characteristics in just a moment.